So, welcome to the third lecture on Atlantis. This one's going to go through how you build the code, how you run Atlantis, and what the input parameter files look like. The best place to start with Atlantis is actually in the wiki. We've tried to put a lot of useful information there. Some of the bigger details are available through these pages. In particular, the documentation is really handy. It's got the manual in it, which I strongly recommend anytime you're looking up any new functionality or a parameter you're missing. I'd check the manual first. If you can't find it there, then by all means search the wiki. It'll let you find a whole bunch of useful information. Any new functionality we add to the system also gets logged in the blog. So that's the first place to start. So if you're looking at how to set the model up, first of all you need to get the code, which comes from an SVN repository. We use a repository so that we can keep the different versions through time. We can go check a specific version from a specific date, or we can log comments to do around the changes. If you're a CSIRO staff member, you have to use a slightly different repository address to the external partners, but both of them are pointing to exactly the same code. Once you've downloaded the code through either Tortoise SVN or Versions SVN or some other SVN client, you can do it from the command line. Then it comes down to building the code. You can build it on many different operating systems. It's now getting quite difficult to run native on Windows because Microsoft, in their great wisdom, changed how they interact with their maths libraries and would have to rewrite the entire code and have a separate branch for Windows and Macs and Linux, which just isn't feasible. So we're starting to use a program called Docker, which basically creates a virtual Linux machine on Windows in a little window, so you can run the same output. If you don't mind running in an older version of Windows, then you can run it under Windows natively. I'll give most of my explanation for the Mac case, just because I'm on a Mac. It's pretty similar on the others. You've got to have a compiler, so on Windows that might be an Microsoft Express. Under Linux, things like GCC. Under Mac, having Xcode is really handy. There's some third-party programs that you need to be able to install. So autoconf, pkgconfig, and libxml all help set up and install basically compile and install Atlantis, whereas netcdf and proj4 are used both for the input-output storage in the terms of netcdf and proj4 for how it deals with the spatial output. The directions should help you step through installing the code. It can get a little bit involved on Macs. It's much simpler on Linux, and then in Windows you use the DOS, but pretty much you download all the programs, you install them, and then to actually build Atlantis, you navigate to where you've kept the code. On Windows, you'd basically be looking inside your Visual Studio if you're in an old version of Windows where you still can compile. For Macs and Linux, you have to do it on the command line. So you go to where you want to compile. The very first time you compile, you have to set up the basically the configuration and the make files and everything. To make that easier, Beck has set up a set of scripts that help step you through that. If you can type and then configure. Once you've set up all the configuration and set up the make files, you can then start to do the installation. So the very first time you make it, each time you want to make clean and clear up after yourself. This means build clean in Windows and clean up, do a make clean in Linux and Mac. Once you've done that, you make it. On my particular machine, I need to do that as a super user. You probably don't need to if you're just making it locally on a machine where you have admin rights all the time. So it'll take a little while to do compiling. All these little messages coming through now are just explaining the steps that it's taking. It's only if it errors out or you get a fail message that you need to worry. And then once you've actually made it, then you've got to install it. So in both cases on Windows, Macs and Linux, it looks like that. Windows is a little bit different. Now, another option that you've got, particularly on Windows, is to use a thing called Docker. So that basically creates a little virtual machine that will do things for you. So you have to have Docker on. And then what you do is, again, you find your way to, in a terminal window, even on Windows, you use a command line to find your way to the main directory where you've got the Atlantis file. So you'll see it's not going as deep as when I just made it before, where I went into this directory. It's sitting one level up, because then you can see there's a Docker file in there. Just because I need to be able to this has a slightly different configuration to my Mac, so you probably won't need to play with the Docker file, the code like I just did just then. You should just be able to do come back to building under Docker, and it's got all the steps that you can follow. So once you're in the right place and you've got Docker open, you should be able just to go make build, and that should trigger Docker, who will now create the little virtual machine and build the code for you, which it's doing right now. So you'll see that it's creating the same little messages that it did natively on the Mac. Okay, so now that it's built on Docker, you should be able to also just run the example model up. Okay, I always get this wrong because I'm not used to using Docker, I must admit. Make run, not build run. Make run. Okay, and now it will just run the example model. If you need to point to a different file other than the simple example model that we've included for you, then you just, while it's doing that, I'll explain what it's doing. It's running in a model in a second. You basically just follow these directions to point it to a file where you want to run a different model other than the example model that comes with the code. Okay, so it's just finishing up the run now. Just give it a couple more seconds. That's done. Okay, so that's the Docker example. For the purposes of the rest of this, I'm not going to run it in Docker. I'm just going to run it native on my machine. So I'll just quickly rebuild the code the way that I want it, just to make sure. Okay, shouldn't take too long to redo. Okay, so the basic structure of the Atlantis code is something I'll go through when we're calibrating things. Basically has a library for each section of the code: the ecology, the economics, the management stuff. We'll get into that in another time. I'll just focus on running the model and the parameter files for today. So once you've compiled the model, you then go to the directory where you're going to run it. So in this particular case, it's the example model. I wouldn't typically keep my run files in the same place I'm keeping the code. I'd put it in a different place. This is just where we keep the example file, so it moves with the code. Now to run the model, if I just get to the place where it is, So sorry, there's quite a bit of junk on my computer. So in the example directory, you'll see there's a whole bunch of parameter files. Okay, so when you want to run Atlantis and you want to know the structure of the command line, you can just type in the name of it. So that's Atlantis main on a Windows machine, or Atlantis merged in Linux and Mac, and it'll give you back the command line. All of these from the -I to the -Q are the required file name. So it has the name of the executable. So on Windows, it'll be Atlantis main. In Linux and Mac, it's Atlantis merged. So it has the name of the executable, and then -I is the name of the input file with a 0. I can show you an example of an actual useful, where is it? So BATS files and SH files are typically how we do it, because no one really wants to type in the very long name. But if we just look here for a second, you've got the input file name and then a 0 because you're just using the first entry of that input file. A -O, then the output file name, a -R, then the run parameter file name, -F for the force parameter file name, P for the physics parameters, B for biology parameters, H for all the fisheries and management parameters, A for any assessment parameters you're putting in, E for economics. This -S can be a CSV or an XML file, which defines the functional groups in the model. Q, again, CSV or XML to define the fisheries file. You also got a couple of optional entries. One is if you want to pipe all of the output to a separate file to keep a separate directory to keep things nice and tidy. And equally, you can keep your input parameters in a different place to where you're running the model. Again, probably for ease of use on large servers more than anything, so you can suck from a home directory and run it in a different spot. This just gives you a little bit of an explanation of what's going on. So just to reiterate, you've got a command line with the different flags and then the different file names. So for instance, this is the run parameter file name and this is the forcing parameter file name. You've got CSVs to set up the configuration of the species and the fisheries, and then in this particular case there's an output folder. So there's a few different ways you then can run Atlantis. One is to actually run it using a scripting language, H1, and so the SH script language will run that command line for you in SH script, and it steps through and runs a model. And that's the exciting way that Atlantis looks when it's running. It just has a time step indicator. If we just let it finish, I'll explain. So that's the time step of the model inside Atlantis. This is the hydrodynamic time step, so you can see how they're aligning. This is the time of year, and this is the percentage of the simulation. So let's see if I can scoot all the way to the top. I can't, so I'll probably run it for a shorter period of time just so I can explain what all those initial things are for. So if we just make it run for 3 days for now, and then I'll go back and I'll run it for a longer period for the output again. So we'll let it load up. So it gives you a whole bunch of warning messages to explain what's happening in the load, and then it runs the model. So if we just scoot back to the top of loading the model. Okay, so this is where we called the run. Now these are what it's doing. It's saying this is how the model's configured. So it's reading in stuff from the run parameter files. Then it goes through looking at the initial conditions files and how many parameters it's got to run through. Every time it gets to a situation where your definition and your information says one thing, but it could be something else for different species configuration, so it's not quite sure if it's an error or just an odd life history. It'll give you a warning rather than fail. If there's any particular parameter that's just not possible, like you've given it a negative depth or something, it will just fail. It's only the ambiguous stuff that it gives warnings on. As it loads in the initial conditions, it tries to warn you anything it's doing a little bit unusually. Some of the nitrogen parameters, it's just saying, look, I'm having to scale those by 0 because of a setting you've put in there. That doesn't make a lot of sense, so you do need to go back and check those. They're intentional errors in this example model so that people have got stuff to learn from. I'll explain what those messages mean in a minute, but it's basically rescaling your initial conditions file to make it a bit easier on you. Then it creates some output files, and then it starts to read in the actual parameters and the forcing files, and that's what all these messages are telling you about as it steps through all of that, and I'll explain those in more detail when we get to the individual parameter files. Then finally, once it's got through all of that, it starts to actually run. It then on the very first time step, it sets up the calendar of reproduction and migration, particularly for age structured or vertebrate groups. If there's anything that seems a little bit odd that it has to juggle in there, it'll give you a warning, particularly with migrating species where it's reproducing or migrating in an odd pattern and it has to juggle the calendar around a bit. Then it runs, and then when it's finished running, it cleans up after itself. Now, we'll just set it back to a longer run so I can show you a couple of other things that it does. One of the things that it does is when it's running, in the output file, it creates a file called delete to halt run. Each time step, it checks to see if it has that file, so that because if it doesn't, it stops the run immediately and tidies up after itself. You can't just kill an Atlantis run midway through because it won't tidy up nicely and you won't be able to read the actual model output and stuff like that. Okay. So if we just run this again for a second as it's running, we'll let it start up, and then we'll delete to halt run, and you can see it stopped immediately and cleaned up after itself. So another way that you can run the model is without using SH. You can actually, you could type it or you could just copy and paste it in. I tend to do it more that way, but the scripting files are really great for creating batch files and sending things off different directions, so they're really handy. Once the model's run, there's a few different output files to look at. We'll get to that in a second. We might just step through the input files first. So there's a whole bunch of input files. There's 5 different kinds of input files, 4 that we use commonly and 1 that's used for forcing some aspects of it. So to start off with the BGM file, this is basically because shapefiles didn't exist when we first started making Atlantis. You can now create these off shapefiles to make your life easier. So you've got the projection of the place that you're in to take from lat long to XY. You've got the number of boxes in the model, the number of faces between the boxes, the maximum depth of the model, the outer boundary of the dynamic part. So you can have extra boxes, but if they sit outside this big polygon, then they're actually just boundary boxes. The only significant rule of Atlantis is that box 0 has to be a boundary box because you've got to store some extra information there, and it's always assumed to be a boundary box. And then box 1 is always assumed to be a dynamic box. It doesn't actually have to be the one stuck up against box 0, it just has to be a dynamic box. Typically box 0 and box 1 are beside each other, but yeah, the only rule is that box 0 has to be a boundary box and box 1 has to be a dynamic box. Now for each box, you give it a name, you identify a point inside the box, typically the centroid, so that you can calculate distances easier. You note the number of boxes it's dynamically connected to, so boxes there's going to be a calculation time step by time step. The number of the face that connects this box to the next dynamic box, and then the ID of that dynamic box. So you can see in this particular case down here, there's a lot more connections, most of them to the same box. It doesn't have to be. You can see in the example down here, there's a lot of different boxes that are touching this particular box. It just depends on the geometry and how many faces you've drawn and how elaborate your map is, basically. For each for each box you have to define its total depth, its area in meters squared. It has a couple of parameters in there that you can use to help continue to tune in exchange rates if the rough hyperdiffusion calculation isn't refined enough. It has the capacity to relax the differential equation solver at a box level if you've got a box that keeps tripping the model up because it gets hypersensitive and you want it a little bit more relaxed in there, just say storms go through and that kind of stuff. You can tailor it at that level. And then these are all the vertices that define the box geometry. After you've defined all of the boxes, you define the faces, particularly the start and end point and the length in meters. A lot of this other information isn't actually used anymore in Atlantis. It's a hangover from how things were done about 15-20 years ago. But if you just use the shapefile to box geometry converter, it actually handles all those for you anyway. The next major file to know about is the configuration file, where it defines all of the groups, species groups in the model. The one for the fisheries is quite similar, not as many things in it yet, but quite similar. It starts off by having a code that you want to use to represent that species inside the parameter file. It can be as many or as few letters as you like, just make it a bit meaningful. It has to have an index. It has to start with index of 0 for the first group. And then the final groups in the model have to be detritus, just by the way that the model's assumed to work. You have all your other groups in between. You give it a name that will be used in the initial conditions file and a meaningful name for plots. You can have a group that's defined turned off and not actually functioning in the model. It's not often the case, but in this particular case we have a lot of them just because we've simplified a bigger model just for the purposes of teaching people in this particular case. For each group you have to have the number of cohorts, so that's the number of age bins for the group. So one for the biomass pools and a little bit of couple for the age-structured biomass pools, and then more for the fully age-structured groups. They don't all have to be 10. In the very original model, it was just a nice compromise between ecological complexity and how very old computers used to handle memory. It's no longer a constraint. You can have as many as you like. I have models with as few as 2 or 3 for very short-lived species and hundreds for very long-lived species like turtles. Each age class needs an age class size, and you can see that for some species that's multiple years. Within each one of these bins it will keep annual increments so that it does the aging transition well, but for the most part the calculations just happen at the bin level. Then you can define the number of genotypes, a number of age stages like juvenile and adult you're tracking, the number of times it spawns in a year, the number of geographic genetic stocks you're tracking, whether it moves vertically, horizontally, whether it's a species that's intentionally fished or one where fishing just impacts it, like in the benthos. So you can see you can have a species that's not intentionally fished but is still impacted. You look at whether it can be managed by a TAC, what actual kind of species it is, so that sends it down the different pathways of behaviour in the code. And then there's just some others saying what its dependencies are and what some of its behaviours is. Is it an aquaculture species? Does it get fed things from outside the model like insects and stuff? If you're using prescribed movement that forces the distribution of the species through a seasonal or annual cycle, you have to put in how many different separate steps or distributional steps like quarterly or seasonally you're going to include. Each of the definitions of these is outlined in the manual, and I'd encourage you to go look at it because this is basically how you set up the core structure of the model. Once you've defined that, then you can go about building the initial conditions file. So this CDF is a human readable version of the net CDF file. That's the initial conditions file. It's just open it with a text editor. It's fine. Just scoot back to the top of the file there. So the basic structure of a netcdf file is it has the file name, it has the dimensions of any arrays in it. So this is the number of our total number of layers, our total number of boxes, and in this particular file there's only one time step. It says unlimited because the time steps could accumulate to be much larger than one. It's only got one currently. If it had 10 time steps, it'd say 10 currently. Your output files are where you'll get quite large entries. A thing to note is here is the second since. That's saying basically what the very first time in the model is. That's anchors time, and any other initial conditions or forcing files that are read in compare themselves against that date in trying to line up which part of the forcing to apply. Then for each variable in the model, it gives the definition of what kind of type of variable it is, its units, any long fancy name it's going to use in plots, and then some other settings that are used within Atlantis. It typically puts all the physical variables at the top, then it'll have all the traces, so the three-dimensional variables, and then it'll have the epibenthic or two-dimensional variables at the end of the declaration. Something important to note, if I just look it up, you don't need to know very much about most of these parameters. You don't typically play with the parameters in the initial condition definition file very much, but a few that are of interest. This is the particle size for those of you who are more into the biogeochemistry kind of things. This is the settling velocity, and this here decay rate is used particularly for burial out of the system. So if you have an excess buildup of detritus, but that is legitimate, but would normally be buried out of the system, that's how you can represent that. Something else that the setup does really well is, particularly in the old days where you had to punch things by hand, there's this thing called fill value, which is a really handy way of setting up the initial conditions. I'll see if I can see one that's got an actual value in it. Here we go. So in this particular case, down where we declare this, we'll have a whole bunch of underscores in the data structure. And anytime it sees the underscore, it will just copy in this fill value. It's not so much used anymore, given we use R tools quite a lot, but it was handy back when they were first defined. So the structure of a netcdf file is that these are the vertical layers, and then it does each of the boxes in turn. If you had more than one time step, it would then repeat that structure for the next time step. It starts with the water column layer, with the layer that's closest to the sediment, so layer 0, and goes up through the water column to the surface. And then it starts again with the sediment. In this particular model, there's only one sediment layer, so it's only got a single column of sediment entries, so to speak, or a single value of sediment entries per box. But if you had multiple sediment layers, you could have even more going deeper into the sediment. So it goes up through the water column and then starts with the sediment and goes down through the sediment in that layering we discussed in one of the earlier lectures. For things that move vertically in the water column, you don't need to put in the three-dimensional structure as much because it'll vertically move them on the very first time step, so you can just drop all your fish per box in the smallest water column layer. For other things where you actually want to have that three-dimensional layer. Okay, so for those where you actually want the three-dimensional vertical layers, you put in the layers you want at the depth that you want them. So you can see here there's only 4 layers in this particular box. You got the surface amount, then you got the layer under that, and then it's just using the fill values, which happen to be 0, I think, in this particular case, or something not very useful or meaningful. It doesn't do it all the way to the surface here because there's actually a couple of empty layers. In boxes, in models where you're using the output of one run as the input for the other one, you can have a lot more detail in this. This is a very simple example, but that's the basic structure of that CDF file. And I'll just reiterate, for the two-dimensional ones, you've only got to put a value per box. You don't have to put a value per layer. Okay, so that's the two main sort of input files. The rest of it is parameter files and forcing files. So we start off with the structure of the parameter files. This is the run parameter file, which basically defines some high-level flags about the kinds of basically the modules of Atlantis it's going to use. All of these flags are defined in the manual, and I'd encourage you to look at the manual to see what they are. This block of ones here trigger, if they're turned on, trigger output into the log file or fprints to the screen and things, printfs to the screen, so that you can help calibrate the model and understand what it's doing. This block defines how long the model is going to run and how often you get output. This defines the size of the model, array sizes. You don't typically play with those, except for the total species number and habitat types. All of this you can get from your CSV file to know which values you need to change there. And then where we were talking about the initial conditions file, it can be a pain to get back into that big file and tweak it if you haven't got quite the right starting numbers, particularly for age structured groups. So this is a little bit of a cheat here. If you have this turned on to 1, it'll use this scaler to just scale up and down the numbers, not the sizes or anything, just the numbers of the age structured groups inside your model. So you can see here there's 2 where we're doubling our species numbers, and these are 0.1 where we're using only a tenth. So it's a fast way of playing with your initial conditions file. But like I said, all of these different things are defined in the manual. The only one I think is worth paying a bit of attention to right now is if the model's not loading properly for any particular reason, get this verbose flag and set the number to a value above 0. The bigger the value, the more it will tell you what it's doing. So in terms of I tend to just whack it onto a 5, and if we just run it for a second with that, you'll see that it spits out a lot more information explaining what it's doing at any particular instant, every parameter it reads in, every value it reads in, and then as it's running it tells you which particular routine it's in at any one time. It does run a lot slower in this mode, so don't do it unless you absolutely have to, and typically you just step through that at the start in getting the model to run, but it is a really handy setting to have. Now in terms of the one other things to be important in here is that when you're first parameterizing a model, Atlantis doesn't expect all the parameters in a set order. It searches by name, and then with the first string that matches that name, it uses the value. So if you've accidentally got duplicate parameters in a parameter file, you're not ever sure which one it's actually using. So it's always good to get rid of duplicates. So once you've set up a model, put 1 here for check duplicates. It'll take a pretty long time to load as it checks for all the duplicates, but you can get rid of duplicates, so you're always really confident about what you're using. Once you're actually confident that all your duplicates are gone, you can go back to 0 and it'll run it much faster, but that's a really good one to go through. Now in terms of the individual parameter files, they're all just flat ASCII files for all of the other parameters as well. They all have a similar structure. They start off with some explanatory text at the top. That's all optional. Then they have a whole bunch of flags that set the overall assumptions in the model. Once again, they're all defined in the manual. For any flags that are needed at a functional group or species level, it uses the same start or end. Most of them are a start, but sometimes they're tagged on the end. Then it'll put a code of the species in question, and then the very first value is the value that it uses as the value of the parameter, the same as in the run file. Then there's a description after the name of after the value, and that can be that's just telling you what's going on. It completely ignores that. You'll see in this particular case there's another value at the end, and it might be a bit simpler down here where you can see there's just 2 values and no text in between. It's only using the first value. The second value is a default suggestion. It's never actually used in the model. I used to try to keep these up to date. They're getting a bit out of date now. Way too much data to try and keep on top of meta-analysis wise, but it's just there as a bit of a suggestion as a default. Once you've gone through all the flags, then you have all the individual parameter values where it again searches on the name and then takes the first value after it as the parameter. There's literally thousands of them by the time you go through the species specific parameters, but there'll be a bunch of parameters in there which go in as arrays, and this is an example here. So it looks for the name of the array, then the first number it finds is the number of entries it's going to expect in the array. It then reads off the next line, which is the values it puts into the array. If it finds more numbers in this line than was defined for the array, it just chops it off at that number. If it finds less numbers than it was expecting, it actually uses the last number to pad out the whole rest of the array. But it will spit out a warning to that effect. So keep an eye on those warnings just to make sure you're reading in what you expect. For the big availability parameter array, you do have to load in line by line, which is a bit of a pain, but it's kind of the only way to do it, unfortunately. So you can see it's a mammoth file, and I'm not going to go through every line of that file. A whole bunch of them you'll never use, but you're still required to put in some kind of value. And then it warns you if that values don't make sense for options you've actually got turned on. If you don't have the option on, it'll still read in a value, but it's just never going to use it. So just pay attention to the warnings that you get on the command line as you load things in. So you can see it can be quite large. There's about 14,000 lines in this particular biology file. The harvest file is quite similar. It has that same kind of structure of the way that it has flags at the top and then parameters with single values for overall global parameters and then arrays for any species or fishery specific. There's a lot of arrays in the harvest parameter file because it's got to do a lot where it's matching individual species per fleet. In terms of the physics parameter file, it again has that same kind of setup. It's got a lot more detail in some of the explanations because I'm not a physicist, so I was leaving myself plenty of messages. Has far few array cases, but the overall general structure is the same. The one that's really different is the forcing parameter file because it's basically a list of other files that Atlantis will need. It starts off by looking for the hydrodynamic files. It then has the temperature and salinity forcing files. It can have some optional recruitment forcing and some nutrient forcing. It identifies other time series that you're going to use to force the model. So that can be nutrient inputs, say from rivers or outfalls. It can be historical catch time series. It can be market time series, contaminants, that kind of stuff. This is where all of that extra scenario definition stuff comes in. In each case, particularly in these time series reads, the structure is that it's looking, well, for the netcdf files and the environmental files, it just wants to know how many files there are, and then also whether it's going to use those files, the number of files there are, the address of those files relative to where you're running the model, and then whether you rewind or not at the end. So if you want to cycle over a file over and over and over again as you run through, so maybe you've only got a year's worth of temperature and you want to run the model for 10 years, you just hit rewind, and at the end of each year it will rewind and let you play it out. For other kinds of model files, you might only want to play through it once. So just say you put in historical catch time series. In that particular case, it uses a slightly different format. It uses a TS format rather than NC format. It asks for the name of what you're doing. No particular reason. It's more to be meaningful for you. A location where it's applying it. In this particular case, it's an XY location in a box and the box number. For the nutrient case, it would actually be the XYZ location that you want to inject the nutrients. Then it asks for the file name and location. I tend to put in dummy files of zeros even for boundary boxes just for completeness sake, but you can just skip the boundary boxes and just worry about the dynamic boxes. At the end of those files, we didn't want to rewind. We just wanted to use the last file continuously into the future. Now, those particular files have their own special format. I've got to remember that it is Now those particular files have their own special format that you've got to remember to open as a flat text file, not as a audio file. Again, new file types have come through since these files were originally invented. Now the format of a TS file is just, you can give yourself a message at the top of what it's about, then you define how many columns it has. In this particular case, it needs these double hashes during the definition. It was just the way the original guy who wrote this set it up. But just follow this kind of thing as a template. So the first column is your time. You'll notice it's got a time since here, and that's so it knows how to align this time series file versus your initial conditions file. So if you're starting your run in 2000 and you happen to have a 1979 time series file, it will actually shift. It won't bother reading in the start of this file. It'll only start from 2000 forward as you project forward. So just keep that in mind when you create the two files. Then for each column, you have to give it the name, which I typically just set to be the code of the thing you want to apply it to, the units that you're reading it in, so in case it has to do a unit conversion, and a missing value, something to apply if you're getting a missing value. So in this particular case, I've used 0. In the old days, -999 was recommended, but it can be ambiguous how a lot of that's applied. So in this case, because we don't want anything to happen if there's a missing value, just put in a 0, so there's no ambiguity. Once you've got all the definitions done, then you have the actual data, which is just tab or space delimited files. One thing to watch out for, particularly is if you've created your files on Windows and you're going to use it in Docker or a Linux instance, is to make sure that you convert it across to be a Mac readable or Linux readable. Actually, Linux readable is the safest. If you're doing Docker or anything, you don't want to be using the Windows format because that really trips things up. They use a different end of line marker that can be hidden. It's not human readable, but the machine gets tripped over by it. So it's something to keep your eye out for. So that's all the input files. Now the output files use much of the same kind of format. There's a lot of flat text file output. So for instance, here's the biomass file. You get different biomass per output time step for different groups. There's netcdf output. So the typical way that you interact with those kind of things is you have R scripts that, for instance, of the type that Javier will go through. So I'll just give you a very quick look now. Javier will go through in more detail, but he's written a bunch of Shiny scripts so that you can look at your runs through time in absolute or relative biomass by age class. There's nothing particularly exciting happening in this particular model, but he'll step through that in more detail. But that's one way of doing it. There are some parameter files from a guy called Shane that helps set up files in the first place, but I'll leave Javier to explain all about the R tools. There are some other output exploration tools. One of those is called Olive. If you're an R person, it's probably easier to use Javier's R tools to do the spatial exploration. I'm a bit old school, so I use this particular very old Python app for looking at the spatial output. I really encourage you to look at the spatial output because that can highlight things that are going wrong. But basically the concept is that it allows you, I think this is one of the species that's on, no, yes, there it is, down in the sediment. So this is a species that lives in the bottom part of the model. So this app lets you look at the vertical and the horizontal distribution of each of your traces through time. You can look through both the water column and the sediments. There's a thing here to pick which sort of vertical that you're looking at. For things like nitrogen or detritus, you'd want to look in both, but it's just a little tool for you to help look through that kind of thing. So There are other things you can do. You can set up your own R scripts for looking through output. I have some Excel files where I compare against data, the model runs of different ones, compare through data, give myself some notes of things I've done, so you can see in past notes about things I've changed as I've tried to fit things. It's completely up to you how you go about looking at the output, but hopefully that's given you some ideas of what might be useful. I think I've gone through all the most useful ways of pulling the files together and running the model. So I hope that's given you a useful introduction. Please don't be afraid of command lines, and then in a future discussion we'll start to go through the code base, but you will need to be comfortable with code. It's not just about being comfortable with command lines. It's nice if you're comfortable with code too, but we'll probably call it quits for today, and I look forward to the questions. Thanks, bye.